So, today we will demonstrate how to measure acceleration due to gravity using compound pendulum. So, this is a very simple setup for computer pendulum, compound pendulum. So, it is a rod and with having many holes. So, you know this simple pendulum, here I can show you, we have used simple pendulum, a mass basically a mass is hanged by a thread. So, here main assumption is that this all mass is concentrated in this bob, and the mass of this thread is negligible. Okay. So, this simple pendulum, here you have thread and you have mass and it is hanged from a support, right. Now, this system is oscillating, right. Actually, here this mass is oscillating and with that this thread is also oscillating. So, this to find out the time period, actually what we do this basically we have to take the oscillation, we have to take the distance of the center of mass of your system from the support. Okay. So, since this mass is negligible, so center of mass, it is expected that it will be the center of this mass. So, distance, effective length of this pendulum we take from here to the center of this one. So, this is the L. Okay. So, and then we time period we tell this t equal to 2 pi square root of L by G. L is this one. So, what is L? L is basically this from where this is the axis of rotation. Okay. So, this is the axis of rotation with respect to this axis of rotation as if it is rotating. So, this is the axis of rotation you can tell. So, with respect to this, so here is the oscillation, is the rotation. So, moment of inertia is important. Okay. Moment of inertia is mass into distance. So, here this distance is basically from here from axis of rotation to the center of this mass. So, this is m L square. Okay. Now, imagine that it is not now is not a massless, it has mass. Okay. Now, when it is oscillating, so not only this mass is oscillating, each part. So, this mass is distributed over this length. Okay. And each mass is oscillating, Now, moment of inertia of this system, of this setup will be different. Okay. So, because now center of mass of this system will not be this one, it will be somewhere some other places. Okay. So, we have to find out the center of mass of this. When mass is distributed, we have to find out the center of mass, and this center of mass now the center of mass is basically now oscillating. Okay. So, so that distance we have to take from here to this center of mass, that distance we have to take. So, this the so if all mass is concentrated in the center of mass here, okay, then it is oscillating. Okay. So, what is the moment of inertia of this system? So, that is basically we express in terms of it's called this I will tell you that radius of gyration, that is the that at which distance this all, if you concentrate all masses. Okay. So, if only that mass is oscillating, so whatever the moment of inertia, now for the whole system the moment of inertia there is the same as that one. So, then that distance is called radius of gyration, right. So, that we have to take care in the case of compound pendulum. So, compound pendulum is basically this, what is this? This is basically this equivalent to simple pendulum, only difference is that this thread is not massless, it has mass. Okay. So, now let me show you. So, this I can take, this is a, this I can take as a compound pendulum. Okay. So, I have to find out first the center of mass of this rod. Here we have taken rod, you can take any shape. Okay. It is not necessary that you have to take it is a regular shape, you can take of any shape, but you have to find out first center of mass. Okay. Now, to find out the center of mass, so we have some arrangement here. So, we will put it on a sharp edge, we will put on a sharp edge to, and then get the balance point, okay, just you can check it. So, efficiently one has to do. So, I think let me try to make okay. So, it is a more or less, this is the center of mass of this rod, this is the center of mass of this rod more or less, but more precisely you can do it, So, you have to just try, no, it has gone. Yes. So, this is the center of mass, I have to mark it, okay. Yeah. So, more or less I think, but that is Anyway, I think it's one has to try to get this position. Okay, one has to, more or less I got it, more or less I got it. Okay. So, this is the position, this is the position for the center of mass. Okay. So, then I will mark it with marker, I will mark it with marker. So, I think I will take a scale, I will mark it with marker. Okay. So, I have marked it, I have marked it. So, this is the center of mass of this rod. Okay. So, to find out after finding out the center of mass, so I will just hang it. So, this is the basically we will take as a axis of rotation or oscillation. So, this so we have arrangement to hang it, we have arrangement to okay. So, we have arrangement to hang it. So, I have hanged it. So, here I think I could just show you once more. So, this total length of this rod is basically this exactly 1 meter, exactly 1 meter. So, this scale is, you see, this in millimeter, 100 millimeter means 10 centimeters. So, up to 900 millimeter means 90 centimeters. So, this is the 1 meter. So, this scale, this length of this rod is 1 meter, 100 centimeter, and you see the just center of this each hole. So, from here is the 2 centimeter, from here it is also 2 centimeter, and center to center of each hole is 5 centimeter. Here you see this is a it's a 80 millimeter, and here it is 30 millimeter, it's a 50 millimeter, means 5 centimeter. So, this each hole difference distance between this each hole is basically the 5 centimeter, and from this end it is 2 centimeter, and my center is more or less, you see, at the middle is 50 centimeter. So, this is, so if it is 50 centimeter. So, when I will hang this one from this point, so from the axis of rotation, the distance of the center of mass is 50 minus this 2 is the 48 centimeter. Okay. So, that way we can will take different distance of the center of mass from the axis of rotation. So, just initially it will be 48, then minus 5 means 43, then 38. So, this way for different length of center of mass from the axis of rotation, we will measure the time period. So, then with time period what are the parameters related, that I will tell you. Already we have discussed in previous class what was the theory or working formula for this experiment, and there I have showed you that this working formula. So, for this experiment basically we will find out the acceleration due to gravity, that is g, by compound pendulum, and determination of radius of gyration about the axis passing through the center of gravity. Okay. Radius of gyration about the passing, so about the axis passing through the center of gravity. So, center of gravity is there, this one. So, axis passing through the center of gravity, okay, that axis also is parallel to the axis of rotation. This is the axis of rotation. So, this parallel and passing through the so basically this radius of gyration, it is coming that from there, as I told this whatever the so this is the center of mass. If whole mass is concentrated here and this other things, you can think this, there is the mass like it is threaded with, is the thread like things, massless. So, then this would be the just its the moment of inertia would be this total mass concentrated here, that into this distance L square. But since mass is distributed, so then this radius of gyration, that concept comes as well as this. So, there basically this mass at the center of concentrated at the center of mass, this into the distance square, that is plus is the basically following the parallel axis theorem, plus the moment of inertia of passing of the body passing through the center of gravity, the axis passing through the center of gravity, with respect to that what is the moment of inertia of this system. So, that as well as the distance from their distance from the axis of rotation to the center of mass, that is square of that and mass of this system. So, this together will be basically the total moment of inertia of our this system. So, this compound pendulum and simple pendulum, this in compound pendulum, this in moment of inertia two parts. Okay. One is just like simple pendulum, okay. All masses is concentrated at center of mass, and this other part is weightless, massless. Okay. So, that part is there, and another part will be there, that mass is distributed over the length. Okay. So, that is covered by the radius of gyration, okay, from the concept of radius of gyration. Okay. So, that is what this this t equal to 2 pi square root of L by G. So, that is the simple pendulum, and in case of compound pendulum, this working formula basically it comes. So, from here you can find out this G equal to basically 4 pi square L by T square, 4 pi square L by T square. Okay. G equal to 4 pi square L by T square. Okay. So, these are also compound pendulum, this same formula we use. Now, as I told, the effective length, this L is effective length of the equivalent simple pendulum. Okay. Equivalent simple pendulum. So, this length is not just length of the center of mass from the support, from the axis of rotation. It is the as I told this, there will be two parts. One is this mass, one is the distance of the center of mass of this system into this square of that distance into this mass of this body, plus another part this coming from, as I told, this radius of gyration. Okay. So, this effective length L is not the length of the center of mass, it is basically this length will be like this. So, here this length L is basically this L plus k square by L. So, how this comes that I already in previous class I have described. So, L is basically effective length of the pendulum, which is equivalent to simple pendulum. So, effective length will be the length of the center of mass plus k square by L. So, this k is radius of gyration. Now, this is a quadratic equation of L, okay, and if you solve it, so it's come L equal to L1 plus L2 and k will be equal to square root of L1 L2. Okay. So, so as I told you earlier in previous class that basically in this experiment we have to measure time period t and effective length L. So, to get the effective length L, actually this will be equal to L1 plus L2, and thereafter if you want to find out the radius of gyration, so it is the square root of L1 L2. So, basically we have to find out L1 and L2 as well as time period. Okay. So, here whatever plot I have shown you, so this is the distance of center of gravity from the axis of rotation. So, if you vary the distance of rotation, distance of this center of gravity from the axis of rotation at different distance, if you measure the time period and if you plot in both side when increasing or other side also, both side if you measure and if you plot it time period versus this distance of the center of gravity from the axis of rotation, then you will get this type of curve, symmetric curve with respect to this center of gravity. And if you just take a parallel line of this x axis, so it will cut these 4 points, So, L1 basically from the this is the line at the center of gravity. So, from the center of gravity this first point, these are basically L1, and from center of gravity this second point distance, this is the L2, or other side also L1 L2. So, generally what we do, we measure this divide by 2, that will be L1, and this distance between these 2 points divide by 2, that will be L2. So, from this graph basically we will find out L1 and L2, and from there we can calculate a capital L, which is effective length of the pendulum, and then radius of gyration, of course, you can calculate taking square root of L1 L2, and for each length we have to take the time period. That is what. So, L will be available to you. Now, here also one can basically, so there is a graphical method. To find out L by T square also, that I will discuss in next class when we will analyze the data. So, what is our task? Our task is vary the distance of center of gravity and will measure the time period. Okay. So, that is what we have to just experimentally we have to do it, and then rest of the part we have to analyze the data. So, let us see how we will measure the this time period for each distance. So, here at present position, so we will note down this distance of the center of gravity is 48 centimeter. Now, at this length I want to measure the time period of the oscillation. So, I will start just disturb it. Okay. So, it is doing just twisting. So, to avoid this one, basically we have to do slightly other arrangement. So, we have to use basically some nut are there. Curve is yes. So, yes, so just I have nut, I can just yes, okay. So, we have to so there should not be any relative motion between this axis and this one. So, this axis itself will just yes, I think this I have to put. Yes, maybe now is yes, now nicely it is just oscillating. Now it is oscillating. So, again to find out time period, you know this 1, 2, 3. So, this way you have to take time period. So, this now this in my stopwatch it is a 0. So, this again least count of the stopwatch is 0.1 second. So, I will just start 1, 2, 3, 4, 5, 6, 7. So, this way you take around 30, 40, 50 oscillation, and then you for that number of oscillation what is the time you have to count. Okay. So, this is the one data for a particular length. Then I have to do for other length. So, I will put here, then it will be 48 minus 5 means length will be 43, then next one 38. So, this way I will go, and you see if I will show you. If I put here, is the distance of center of is the I think this is the 48 to. So, how much it will be? It will be 500 2 was a 48, and then from there 48, and here no. So, this one 500. So, if I put here, so this 48, 43, then 38, then this will be 33, then 28, then this will be 28, and then this will be 23, and then this will be 18, this will be 13, this will be 8, this will be 3. So, from here the distance will be 3, So, taking this distance, let me just show you one. No, I think yes. So, if I take this one, I think other side I have to take, because yes. Okay. So, now distance at 48 distance we have seen, now it is 3. Okay. So, this it is expected that this time period will be very large, time period will be very large. So, my watch is ready. So, I will start this oscillation. You see, okay. So, I have to keep it properly. Yes. Just I am showing you method, because one has to do carefully, okay, taking time. So, just slightly longer if I put, okay, it's the twisting. Anyway, so one can see this, time period. If I just start to take it, 1, 2, 3. You can see this earlier when I was counting 1, 2, 3. Now I am telling 1, 2. So, it is very slow. Okay. So, this side we have taken the reading for it. So, now what we will do, we will take the reading in reverse side. So, because in graph I showed this in both side, okay, starting from the center of gravity. So, distance from this side and distance from the other side also we have to take, only then we can draw this symmetric curve. So, we will do the experiment from the other side. See, in same way we starting from the top here, other side starting from the top, here I will do experiment. Okay. Okay. So, again center of mass from the other side I am taking. So, take this same way as yes. So, you see how fast it is, and when this length was decreasing, so it is so slow. So, that is what this graph was telling, that it should be like this. So, just measure the time period for 30, 40, 50 oscillation and take the time. So, you have time period t. So, total time noted down here, that will be that number of oscillation divided by number of oscillation, that will give time period. Okay. So, t will find out for each length, and for each length this 48, 43, 38 etc. So, you have so we will plot the distance from the center of gravity, okay, 5. So, I think starting from 3, then 8, then 13, then 18, for each what is the time period. So, we will plot the graph and we will see this symmetric curve we will get, and from that curve we can find out L1 and L2. If you find out L1 and L2, you will find out the effective length capital L and the radius of gyration k. Okay, effective length capital L equal to L1 plus L2, small L1 plus L2, small L2, and radius of gyration k will be square root of small L1 L2. So, L1 and L2 you will get from this, from the curve wherever data you got from this measurement. Okay. So, this data analysis will continue in next class. Thank you for your attention.